Communication Engineering of Indian Institute of Information Technology, Guwahati, and she's specialized in wireless and mobile communications, MIMO systems, wave communications, etc. And she will be talking about the security in millimeter wave systems for 5G cellular. Dr. G. Aruna has taken a PhD from IIT Guwahati in the area of electronics and communication, wireless communications, and ME from Anna University in communication systems. And from a profile, we could understand that she's an expert in wireless communication systems. And with this information, I invite Dr. G. Aruna to handle the present session. Thank you.
Thank you, sir. Thank you so much. So good morning, everybody. I hope I'm audible to all of you.
Yes.
So today's topic, my topic will be security in millimeter wave systems for 5G cellular. So in this topic, actually, first I'll be explaining the generations of mobile communications and what is the importance of 5G, then how we are entering into the millimeter wave systems. Then finally, I have included a little bit of security, how the security is maintained in this millimeter wave systems. So starting with, this is the outline of my presentation, starting with the introduction, the wireless evolution, how we have reached, or starting from the basic step, how we have reached to 5G. So that, and advantages and disadvantages of using 5G. So how we are entering into the millimeter wave. So why the millimeter wave should be used, or what is the importance of millimeter wave? Of course, what is the antenna structure? What is the propagation mechanism used in millimeter wave? And all those topics will be discussed. And of course, the main concept of millimeter wave is bandwidth. What is the beam with interference resistance? So the security lies in how we are forming the beam width and how it is interference resistance, and what is the propagation behavior. All the issues are will be presented. Okay, so starting with, I am starting from the basic, because many stream people are here for this FDP. So let us start from the basics. So here we can see that there is a global bandwidth shortage. So for high-end applications like real-time video transmission, we are having a bandwidth shortage. What should we do is we should overcome this bandwidth shortage. So for overcoming this bandwidth shortage, we are implementing lot of technologies. So one technology is the millimeter wave technology, and other technology is the large intelligent surface technologies. These two technologies are more prominent technologies in the 5G communication. So here, actually, the concept of this millimeter wave and large intelligent surface technologies are mainly to use the properly and to increase the data rate. Okay, so for high-end applications like real-time video transmission, real-time video watching in mobile, while the user is in mobile, the high-end application when the users are in mobile is executed by this millimeter wave technology, where a high capacity is achieved, or a very high data rate should be needed. So here the wireless service providers are facing many challenges. So whenever you are going from wired to, what happens is the challenges are interference between other users, and when we are sharing and other SMS and some data, there are a lot of opportunities for tracking and many things like that. So there comes the security issues. So let us see one by one. So here the carrier frequency spectrum is between 700 megahertz to 2.6 gigahertz for the wireless communication. So here different technologies fall in different frequency range. For example, the GSM or mobile communication which we are using is falling in the range of 700 to 900 megahertz, and later for higher end technologies like this millimeter wave systems, the frequency range increases. The frequency range increases to 2.6 gigahertz to 70 to 80 gigahertz. So in that case, when the frequency range is increasing, so many challenges will arise, starting from the transmission to the antenna array structure and the absorption in the environment. See, for example, if the frequency is increased to 25 or 5 or 6 gigahertz, what happens is the absorption of the signals by the environment due to rain or due to the particles in the environment becomes more. But actually, when we increase the frequency, we are having lot of advantages. That advantages also we'll see what are the advantages for going for the higher end frequencies, and also what are the disadvantages. So initially in this talk, I will explain what is this millimeter wave systems. So only if we understand the millimeter wave systems, we can go for the security issues. So here the wireless service provider requires simultaneous management of multiple technologies. As I told, when we are increasing the frequencies, the service provider headache is to face many challenges. So let us see one by one. So this is a photography of the base station. So now this base station should be working in any of the generations. So we are having so many generations in mobile communication, starting from the first generation, second generation, third generation, fourth generation. Of course, we have reached the fifth generation. So the base station should be compatible between any of the generations. So here the mobile base station networks need to support a higher data rate requirement. So why the higher data rate is required is to go for the real-time video and higher end applications. We need a higher data rate. So that is understood by everybody, higher data rate. So for achieving a higher data rate amidst of all these challenges, it is very difficult, or it is very difficult to execute this. Okay. So here, efficient radio access technology combined with more spectrum availability is required. Excuse me. It's yeah, sorry for the disturbance. So the mobile network needs to support higher data rate. Why the higher data rate is required is we have to applications which requires the higher data rate. So our challenge is to make an efficient radio access technology which is combined with more spectrum availability. Okay. So now, yeah. So here, how we are going to achieve a larger bandwidth and higher data rate. So this diagram shows you like, this is the frequency spectrum. So here, so different applications lie in different ranges of the frequency spectrum. So the left-hand side shows you the microwave frequencies, and right-hand side shows you the millimeter wave frequencies. So here the GSM mobile phone and all other lower applications lie in the microwave frequencies. So the satellite communication lies in the 20 gigahertz. That is, these a little bit higher applications are falling in this range. The frequencies which is used for radar and satellite communications lies in this range. So when we are going for the higher end communication, so we are using the spectrum which is available between this range. It is in the range of 50 to 100 gigahertz. So these are called as the millimeter wave frequencies, or the communication which is happening in this range of frequency is called the millimeter wave communication. So here it is highly required for the 5G wireless networks. So keeping this in mind, let us go to the different generations of the wireless communication. So the first generation, what is happening in the first generation? In first generation, the protocols which we used is the frequency division multiple access. So here the applications were very limited. The key features were it was analog. It was not the digital transmission. It was an analog transmission. So we had only the voice transmission, or the communication between different people was primarily the voice communication. So the security here was very, very less. It was very less secured. Okay, and the low bit data rate. Of course, only voice transmission means we are having only a low bit data rate. So here we are having the access to roaming for single type of analog wireless network. So here the networking was also in the form of analog, and we didn't have much of roaming. We didn't have any digital technologies. We had only analog technologies, and the main communication between the users was only primarily the voice communication. Next, we are going for the 2G and 2.5G, where the access protocols are time division multiple access and code division multiple access. So here from analog to digital, we are moving from analog to digital. So here the security is more, it is more secure. A little bit of security we introduced. So here the communication between the people was increased from primarily voice to voice and data. Okay, so here we are having the access of roaming. And of course, the network issues were also digitized. Earlier, the network issues were analog. Later, the network issues were the digital wireless networks. So 3G and 3.5G. Next is the 3G and 3.5G, where we are having some technologies called the CDMA 2000, CDMA. And of course, I'm not going in depth to these technologies. Maybe the outline I can tell you. So here in FDMA, what we do is the different user data are transmitted in different, using a different carrier frequencies. Okay. And in the end, in the receiver, what we are separating the data of different users by tuning to that particular carrier frequency. So this was the main technology which was used for FDMA. So in the first generation, we are using FDMA, where we are using the frequency division multiple access. So multiple access means accessing the data of different users or multiple users, accessing the data of multiple users. So it is executed by frequency division. What do you mean by frequency division is the data of multiple users are transmitted through different carrier frequencies. Okay, and in the receiver, what happens is we are tuning to that particular frequency to obtain the data of different users. So here security was a big challenge in this frequency division multiple access, because we did not have any other technique to combat the interference. Okay, so here the security was the biggest challenge, and we had a very, very little security here. Next, time division multiple access. Here the data of different users are transmitted through different time slots. Okay, the data of different users are transmitted through different time slots. So here synchronization was very important. So after this 2G, we are not going for analog. Everything is going to be digital. So here packets. So here we are transmitting the data of different users in different time slots. Okay. So here in the receiver, then we can separate the data of different users by synchronization, and there are many methods to execute the time division multiple access. Now, code division multiple access. What do you mean by code division multiple access? Like different users' data are being separated, or they are being identified, or they are being transmitted separately by using different codes. Okay, so here we are generating different codes, and we are combining the user data with that particular code, and then we are transmitting. Okay, in the receiver, what we are doing is we are obtaining the data of the receiver by removing the code. So we are having a different technology where we can remove the code and separate the data. So here, if you see in the first generation, the data and frequency are being combined and transmitted. In the second generation, TDMA, the data and the time slots are combined and transmitted. In CDMA, the data of the users and different codes are combined and transmitted. Okay, secure. The security in the code at a very, very higher end. So how I can say that the security is very higher end is for each and every user data, one particular code is generated. So that particular code is very unique. Okay, so that particular code is very unique. We are having a lot of circuits for generating the code for each and every user. Those circuits, I'm not going to show it here now. For example, we can say a pseudo noise code. We are having a pseudo noise code which is generated for the data of each and every user. So that particular code will be very, very unique for the particular user. So only if the receiver is having that particular code, it can decode the user data. Okay, if the code is not available at the receiver, you will not be able to decode the data of that particular user, even if one bit changes. So digital means everything is going to be ones and zeros. In a single bit, it will not be possible to retrieve the data. So here the security is very, very high. It is more secure. So here in code division multiple access, as I told you, any other user will not be able to retrieve the data of the other user or the desired user, because the code which is generated for all the users are different. Okay, so this is very security wise, code division multiple access was a very, very 3G, which is having CDMA, and anyway, these are the subdivisions of the code division multiple access. Here you are using digital, the global roaming access or wireless networks, everything is used. Anyway, then after that we are going for 4G, we are going for the orthogonal frequency division multiple access. That is actually you are transmitting the data of different users by through the different carrier frequencies. It is same as FDMA, but here we are using a little bit of orthogonality. Okay, orthogonality between the frequencies. So keeping these generations in mind, let us go to the 5G. So including all this, now we are going to the 5G wireless. So in 5G wireless, basically what we are going to do is, so the frequency, carrier frequency allocation is in the millimeter wave range, means in gigahertz. So when we are talking about gigahertz, the first thing which is coming into picture is the antenna size. So here only I will tell you what will be the antenna structure of the millimeter wave. Okay. So here, since the frequency is in gigahertz, you can, the antenna size will become very less, because they are related by the equation lambda is equal to C by nu. Okay, lambda is equal to C by nu, where lambda is the wavelength. So the antenna height is based on the wavelength only. So here, when the frequency is keep on increasing, that is in gigahertz, the wavelength will be decreasing. So that is why it is called as the millimeter wave. Okay. So the antenna size will also, it is directly proportional to the wavelength. So as the wavelength is decreasing, the antenna size also will decrease to a very, very greater extent. Okay. So here this, please keep in mind, this is the main feature of this millimeter wave technology. Okay, this is going to help us in keeping the data secured. This particular point only is going to help us to keep the data secured. Okay, So throughout this topic or throughout this talk, we will be having the millimeter wave technology, where the antenna size is going to be very, very small, because it is directly related to the wavelength, and wavelength is again related to, inversely proportional to the frequency. So please keep this in mind. So here, another key feature of this millimeter wave is we are going to generate a highly directional beamforming antennas. So by this, we are going to ensure the security of information. So I will show you like how the data is being transmitted for in the RF, I mean in the GSM, in the ordinary mobile communication, in the 4G, and how the data is being utilized in the 5G wireless. So two main concepts. One is the antenna structure, and other one is the highly directional beamforming antennas. So the antennas are going to be very small in size. So since the antennas are very small in size, they are going to be fabricated in a chip. Okay, they are going to be fabricated in a chip. So once the antennas are fabricated in a chip, they are going to transmit the data in a highly directional beam. So this highly directional beam is going to give us the higher data rate. Okay, instead of transmitting rays, we are going to transmit the high directional beam, which is going to give a high data rate, and thereby we are going for the higher end applications. So next are all our this IP networks. We are going to do the packet transmission, and of course the quality of service is going to improve. So please keep in mind throughout the talk, the first 2 points. One is the antenna, and other one is the highly directional beamforming. See, advantages of 5G. So 5G is no more the ray transmission. We are going to have the beam transmission only, which is going to provide us the highest capacity and the highest data rate. We are going to have a long battery life, a very low infrastructure cost. But the complexity is going to be more, higher data rate, it is more efficient, it is highly reliable, and security wise, it is going to be very, very highly secured. In the later slides, I will show you how the security is maintained because of this beamforming. So now, so backbone of the wireless network is 5G, which will move from copper cables to the fiber optic cables to the millimeter wave wireless communication. So copper cable is not being used anywhere. So now we are going for the optical fiber cable. That also is, secured, but everywhere we cannot implement the fiber optic cable because of its complexity and because of its cost. Okay, the optical fiber cable is very, very costly. So everywhere we cannot lay the optical fiber cable. So we are going for wireless, which is the millimeter wave wireless communication. So let us go to the next thing. So the next generation wireless technology, which can provide up to the multi-Gbps wireless connectivity. So the data rate is expected to be 40 to 100 times faster than today's wireless LAN technology. Okay, so the data rate is expected to be 40 to 100 times faster than the today's wireless LAN technology. So next is the advantages of millimeter wave. So frequency range is from 25 gigahertz to 300 gigahertz. As I told you, so if this is the frequency range, the wavelength is between 10 mm to 1 mm. Okay, so depending on which frequency we are choosing, the wavelength lies between 10 mm to 1 mm. So what is the advantage of using this? Okay, so more bandwidth is available. So in this range, more bandwidth is available and higher data rate is achieved. So the radio spectrum is still rather underdeveloped. It is underdeveloped, but still we are going for this frequency range for many of the issues like this higher data rate. So in 1970, the military applications were implemented using these technologies. In 1980 itself, the millimeter wave technology was implemented for commercial applications. So this millimeter wave technology above 40 hertz was implemented in 1990. Anyway, these things are not very important. So we are having a saturated spectrum between 700 megahertz to 2.5 gigahertz, which we are going to use. So, okay, fine. So now we are coming to the architecture of this millimeter wave technology. So please see, you can see that we are having a serving base station, and from the serving base station, we are going to communicate directly to the users. So with this serving base station, we will be having a millimeter wave base station, which is the small red tower, which is having a millimeter wave base station. With this is called the backhaul, which will be communicating with the serving base station. Okay, and then next we are also having a millimeter wave relay. So when all the base stations are going to work on this beam technology only. So I mean, here no ray technology is going to be implemented. We are going to obtain a very high data rate. Okay, so here you can see that we are having the relays also. We are having in between relays also. So whatever is the base station, both uplink and downlink, all the communication links are going to be implemented by this beam technology only. So you can see that the mobile users. So when we are going for this kind of technology, the distance between the mobile user and the serving base station is not going to be more. Okay, so these are short range communications. Okay, see, that is why here it is written as NLOS communication. NLOS communication is the non-line of sight communication. Okay, non-line of sight communication means the distance between the user and the base station is little bit more. So line of sight communication is the range or the distance between the base station and the user is very, very small. Oh, these are called the short range communications. So here when we are talking about the security issues are very, very high, because jamming and obtaining the signal is going to be very, very difficult, because the transmission is not going to be very far. The base station and the users are not going to be very, very far, so that we can track the signal in between. It is going to be a very short range communication, keeping that is one point. The communication between the user and base station is going to be very, very short range, and the data transmission is going to be over a high beam. Okay, so that beam cannot be easily accessed by the other people. So that is a very important issue here. The beam between the serving base station and the mobile cannot be easily accessed by the other people, because we are including a lot of hardware and software technologies to generate this beam. Okay, in the later slides, I will show you how the beam is generated. So there itself, the security issue will be handled. Okay, so here one point is the distance between the base station and the mobile is very less. That is one thing. And the data transmission between the base station and the mobile user is going to be very high, generated by the high capacity beam. That is second one. And thereby the security is very well maintained, because the beam transmission between one user and the base station is very, very different from the beam transmission between user 2 and the base station. Is it clear? So keeping these 3 points in mind, we can implement lot of security control. Means like when the data transmission itself is going to be very unique between the user and the base station, there is no much need of implementing security issues. Okay, when the beam itself is going to be very unique, then there itself our security is going to be handled. Okay, so see here, So this is called the directional beamforming. So this is the key feature of our millimeter wave systems. We are going to have a directional beamforming, or here we can call it as the beamforming coding. So this is the internal structure of the base station. Okay, internal structure of the base station. So in the base station, what is happening? So beamforming, pre-coding. Pre-coding is the internal structure of pre-coding is not necessary to be shown now. So the base station, what is happening in the base station is, so this is the antenna array structure. So you can see that antenna arrays are, you are going for a massive MIMO antenna structure for this millimeter wave. Massive MIMO is, we are having here the antenna pattern which is showed is 4x4. Okay, 4x4 antenna pattern. Okay, 4x4 antenna pattern is shown here. But generally in the base station which is practically used, we'll be having an antenna array of 128x128 antenna arrays. Okay, so these small circles are the antennas. These small circles are the antennas. They are fabricated on the chip. Okay, so these small circles are antennas and they are fabricated on the chip. They are controlled by some security. So definitely you should having some controlling pattern, so that you can orient the beam to user terminal 1, user terminal 2 and user terminal N. One second. Yeah. Yes. So these antenna array pattern is shown here. It is 4x4. But basically in our base station, which is practically used for our today's mobile communication, we'll be having a very, very huge antenna structure. So the antenna patterns which are fabricated on the chip will be 128 cross 128 antenna structure, or even more. So here behind this circle, in the circuit wise, behind the circle, in the circuit, we'll be having a circuit which is going to control the ray transmission, which is going to control the transmission of the rays. Okay. So now different technologies are applied. How we are going to implement this transmission, that also we'll see in the future slides. So here we are having high gain links between the base station and the handset. So this diagram, if you see, it is shown in the form of beam. That is why it is shown in the form of beam. So it is stream 1, stream 2 and stream N. So each are different colored because they are unique. And it is reaching the user terminal 1, it is reaching user terminal 2, and it is reaching the user terminal N. So if you see here, the user terminal 1 cannot access the stream 2. User terminal 2 cannot access the stream 1. The technology is implemented in such a way that the security is very, very highly maintained by generating this beam. So if you are using the ray transmission, it is very easy. It is very easy to access the rays, and interference is also more. So here what happens is the interference is very, very much minimized. Okay, it is very, very much minimized because we are implementing the circuit in such a way that the data is unique, and the data can be retrieved only by the user terminal 1 or 2 or N. So that also I will explain you how we are doing it. Okay, so at this point, I would like to mention that user terminal 2 cannot access the stream 1, user terminal N cannot access any other stream. So thereby the capacity is also achieved at a very, very high data rate, and the data is also secured. Okay, so this is the antenna array pattern going to the high gain links between base station and okay. So here So this is the difference between the microwave communication and the millimeter wave communication. So here in microwave communication, here the beam is very, very huge, and in millimeter wave communication, the beam is very narrow. So I will explain you how this beam is being narrowed. Okay, how the beam is being narrowed. So by narrowing the beam, what are the advantages and how the security is maintained? Okay, so here narrow beam width, approximately 2-degree beam width, and microwave is actually simply you are transmitting it by any number of antennas, and in the receiver you are implementing, I mean we are implementing so many antennas to receive it, and in between the transmission, that is between the user and between the antenna of the receiver, between the base station and the antenna of the receiver, we don't have any control. We don't have any control between the base station and the user antenna. Whatever we have transmitted is transmitted. Type of technology for security in between. Of course, we are having the cryptology keys and everything, that is different. We are not I mean, we are doing a little bit of security issues, but not as good as in millimeter wave. Okay. So here, if you see in microwave, the main problem is the interference. So when the beam is very wide, physically itself, you can understand that there are a lot more of interference. So in millimeter wave, first thing is we are reducing the interference. If you see the beam pattern, which is given in the diagram, it reduces the interference and spectrum reuse can be done. The same beam can be used for other users. Not the data, but the in time basis, you can use it for spectrum reuse can be done for other users also. So polarization techniques are used. The waves are highly directional. I told you already, like the waves are highly directional. It offers very, very high security. So again, at this point, I would like to mention that by implementing this technology, we are able to obtain a highest security. By using cryptographic algorithms, the networks can be further secure. This is the main key. Then apart from this, we are applying some cryptographic algorithm, and further it can be secured. So here, please look into this diagram. So initially, as I told you that initially in microwave, the transmission is omnidirectional. So when it is omnidirectional, if you call it as omnidirectional, the radiation pattern is given in the form of a circle. So antennas are small, it is in millimeter wave. So highly directional MIMO system. So here I would like to tell a little bit of this MIMO transmission. So here we are having multiple input and multiple output. Okay, no more we are dealing with single input and single output, because that is not enough for our data rate which is achieved. We want a high data rate to be achieved. So to obtain a high data rate, we have to transmit a beam. So how can we go for a beam? So this circle has to be converted into a beam. So how can we go for that beam? So by the only method to achieve the beam is by using the millimeter wave technology. So how can we go for this millimeter wave technology? By increasing the frequency, thereby reducing the wavelength, and thereby reducing the antenna size, and thereby fabricating the antennas in the chip. Okay. So this is the diagram which shows you the difference between, the omnidirectional antenna pattern and the beam pattern. Okay. So antenna geometry is at the chip size. So here we are reducing the fading, multipath and interference. So 3 things are taken care. Fading is nothing but as the signal is transmitted, the signal will be lost because of the obstructions in the environment, because of thunder, lightning, because of rain, because of many other noises which is generated in the link. They affect the signal. So that fading can be completely handled by this kind of technology. Multipath is the signal will be taking different paths. So if you are not going for a highly directional MIMO transmission, the signal is going to take any path, whichever it is needing. Whatever path it wants, it will be taking. You will not have any control for this transmission. So it will be taking any path whichever it wants, and thereby the interference is also increasing. So the antenna geometry is at the chip size. So these things I wanted to mention here. So here, see, this is the physical size of the antenna becomes very small. So complex antenna arrays can be built and you are integrating it on the chip. So you can see the fabricated antenna in this particular diagram, which shows you the photo of how the antenna is being fabricated. So you can do this by, so 128 cross 128 antennas will be fabricated and it will be put in the base station. Okay, so again, this is a propagation mechanism based on the principle of this line of sight path. It is required to use the reflective paths by many objects. So you can see the line of sight link. A line of sight link is straight, and reflection also will be there. The signals can be blocked by the buildings. So everything will be taken care by this millimeter wave technology. Again here, so I wanted to show you the difference between this technology and the directional beamforming. Okay, so here if you see, we are having n number of antennas in the transmitter side and n number of antennas in the receiver side. The structure also can be varied based upon our requirement. The structure, antenna structure, can be changed. So the steering antenna is required and smart antenna. These antennas are called as the smart antennas. Okay, again, talking larger bandwidth, higher transmission rate, capability of the spread spectrum, and is more immune to interference. Okay, these things I have already told. So now I am going for the real security, whatever we have worked in. So here, one of the main disadvantages, the cost is very high in manufacturing. So extremely high frequencies are having significant attenuation. As I told you, the main disadvantage in this millimeter wave technology is the oxygen absorption and the rain absorption. The environment will absorb the signal more. But you know that every technology has a bottleneck, and every technology will be having a will be having a drawback. So any technology will be having both advantage and disadvantage. So here, even though we are having significant attenuation, the attenuation will be more compared to the microwave. The absorption, signal absorption will be more, but we can go for higher data rate and security in millimeter wave. So we have to sacrifice a little bit if we want a higher data rate and a better security. We have to sacrifice the attenuation. Okay, so here this millimeter waves, long distance applications are also done. So the penetration of power from the millimeter wave concrete wall is known to be less. Okay, see here, interference with oxygen and rain also. As I told you, we'll be having more interference with oxygen and rain. Okay. So security in wave. So for example, see here, this example I had shown you the application of the millimeter wave technology in vehicles. Okay, in vehicles which are already in motion. So here, this can also be called as the vehicular technology or vehicle-to-vehicle communication. So here, vehicle-to-vehicle communication is there, and how the security can be maintained in this example. So here, the data is being transmitted, and this is the receiver. So the data is being transmitted between transmitter and receiver. So here, when you are going for this beamforming, there is no chance of the eavesdropper to hear or to obtain the data, which is being transmitted between the green and the red vehicles. Another point which you have to note is, whenever we are forming this beamforming technology, we'll be having some grating lobes. The grating lobes are called as the main side lobes or the bigger side lobes. We'll be having the bigger side lobes. If you see, the two side lobes are given, which are of higher power. So the power of the main beam width is very high. That I have told you, and we have understood that. So here we'll be having this grating lobes. They are called as the main side lobes, which are having more power. So if the eavesdropper is able to receive this grating lobes, then there is a possibility to access the data. So we have to nullify this grating lobes, or we have to make these side lobes, grating side lobes, as 0. We have to reduce the side lobes. Is it clear? So that I will show you how we are going to do it. So this is an example how I am going to handle the security in millimeter wave communication. This is an example how the security is maintained. So here, now what should I do? I should reduce the side lobes, or I should make the grating lobes as null. I should nullify the grating lobes. Transmitter is there, receiver is there. So the grating lobes should be nullified. Grating lobes means you can see the side two lobes are there. So that I should reduce. I should make it 0, or ultimately I cannot make it as 0, but I can reduce the power of this side lobes or grating lobes. So let us see how we can do it. So apart from this, we are having lot of methods how we can handle the security, but here I have taken only one method, that is this. So see here, we are now handling with the multi-gigabits per second data rates. Okay, fine. Now, from the conventional, we are shifting to a higher frequency, higher data rate, everything. So here, new security challenges are introduced. It cannot be handled by the traditional cryptographic means. So for instance, the lower frequency system, the public cryptographic keys can be simply broadcasted over the wireless channel, but here actually we cannot do that. No, we can do that, but the complexity is a little bit more. Okay, so here the directionality of the wave channel dictates the dedicated public key transmission to all the network nodes. If possible, we can do that, but the infrastructure for key generation and management might not be easily accessible. Why? Because see, infrastructure for key generation and management is not readily available or accessible. Why? Because we are working in a very high frequency. So when the frequency is keep on increasing, the hardware structure, the RF part and the hardware structure is going to, complexity is going to increase. So when my hardware is going to handle a very high frequency, then the complexity of making the hardware is going to increase. Okay, so our main aim or our main motto is the directionality of the millimeter wave. So that we should keep in mind. So public key transmission to all the network nodes is a little bit difficult. So let us see what we can do next. Okay. So with increasing demand of low latency application, increasing size of communication network, implementation of the cryptographic techniques becomes complex and challenging, especially in millimeter wave systems. So why? Because the frequency is more and communication, the network size is also more. So now other methods to enhance security. So keeping the technology of millimeter wave in mind, the methods to enhance security is, one thing is the location based beamforming. So by now, I think I have made clear what is beamforming. Okay. So location based beamforming means now we can make the beamforming adaptive, and we can generally we'll do it like that only. We will locate the user, and we can direct the beam to the user. So that is called location based beamforming. So wave beam design based on hybrid and I mean, we are using a technology called this hybrid pre-coding, which will give us the wave beam. Okay, so what this thing does is the information symbols are transmitted to the target receiver, and the noise is being received by the potential eavesdropper, which are having sensitive receivers. So by doing this, actually the target receiver will be receiving the original data or the information symbols, and the hackers or the eavesdropper or the unwanted receivers, which are having sensitive receivers, will be unwanted unwanted people which are having sensitive receivers will be receiving noise like signals. So it will be jamming. So they'll be receiving noise like signals. So this enhances the security in the millimeter wave communication link. Okay. So here, this is called pre-coding. So this is the baseband structure which I showed here. So S1, S2, S3 up to SK, these are the user datas. Okay, user datas. Then C1, C2, C3, of course, this is some code or something we are implementing, or carrier. This is the carrier which is which we are appending it to S1. I mean, like this basically shows the modulation which we are giving to the user data. Next is the local oscillator. Local oscillator is the baseband signal frequency will be converted to a higher frequency by this local oscillator, which is going to give you the carrier. Anyway, this circuit explanations are, I'm keeping it a little bit less. I just wanted to tell you how the security is maintained here. Okay, so here, if you see phi 1, phi 2, phi 3, phi n. So this is called the RF selection, or this is the phase shift which we are introducing to the data of S1 for transmission. Okay, phi 1, phi 2, phi 3. So this is the shift which we are introducing to the data. So each antenna is going to shift the data, and it is going to transmit it in that particular direction. So now our job is to choose this phi. So our job is to choose this phi, or our job is to choose this phase shift such that all the antenna transmissions are combined to form a beam. So here this antenna array is there. Each antenna array is having a back circuit. It is having a circuit at the back, which will be orienting, or which will be directing the rays at an angle of phi. Okay, at an angle of phi, thereby you are generating the beam. So this is the channel, H1, H2, HK are the channel, and this is the receiver part. Local oscillator, that is the RF modulation and demodulation part, where the local oscillator and the carrier are separated and the data is obtained. So this is the circuit wise explanation of how this is maintained. So coming to the other methods of improving the security. So here, as I told you, we are having so many methods to improve the security. One is the location-based beamforming. So I'm not going, I have explained it, but in detail, I will explain these two technologies to improve the security. First one is the random antenna selection, and second one is the opportunistic noise injection. So this opportunistic noise induction reduces the interference. That definition alone is enough. Like we are reducing the interference here, but the main technology which we can concentrate is the random antenna selection. So we are selecting different antenna subsets for different symbols. Okay, this is called the antenna subset modulation. So the aim of this particular technology is it randomizes the amplitude and phase of the received signal along the side lobe. I already told you, like, our aim is to reduce the grating lobe or to reduce the power of the side lobe. So how we are going to do is by opting for the random antenna selection. So here we are averaging out the signals in the undesired direction by randomization. Okay, by doing this randomization, we are averaging out all the signals in the undesired direction so that any other user will not be able to retrieve my data. Okay, so we can use the random antenna selection to mitigate the inter-user interference. So I'm not going to allow any other user to access my data by using this particular technology. So this is the random antenna selection. So let me show you how I'm going to do it. So the aim of random antenna selection is I am going to nullify the grating lobes or side lobes, or I'm going to average it out. So the fixed antenna selection is antenna subsets are fixed. Each subset should be selected not to generate the grating lobes. I am choosing the subset accordingly not to generate the grating lobe. Significant inter-user interference will be there. So see, this diagram is given here. So this diagram shows you. So the small dots are the antennas. These small dots are the antennas. Why it is shown in the form of dot is the size is very, very small. It is fabricated in the chip. Okay, that is why it is shown in the form of dots. So fixed antenna selection and random antenna selection. So A is the fixed antenna selection and B is the random antenna selection. So here, what is fixed antenna selection going to do? I am picking up 4 adjacent antennas, combining them to form a beam. So that will be transmitting the data of user 4. And other 4 antennas will be combined to form a beam that will be transmitting the data of user 5. So I am doing it like this. So what are the advantages and disadvantages here? Advantages, the complexity is a little bit less, but disadvantage is it is not as good as this random antenna selection. Interference is the grating lobes are not minimized as in random antenna selection. So in random antenna selection, if you see, you can simply pick the antennas for transmission. You can simply pick. So the yellow is here and there, you can pick the antennas. So the yellow shows you like the antennas are chosen for user 3. They are not going to follow a particular pattern. Okay, they are not going to follow a particular pattern, or they are not going to be fixed. The pattern is not going to be fixed. Okay, so you can ask me a question like, what is the advantage of doing this? By doing this, we can orient the direction of the beam, and the side lobes or the grating lobes can be nullified. It can be reduced. Okay, so that is the aim of doing this. So it is dynamic. So instantaneously, I will be choosing the antennas for transmitting the data. So see, you can see here dynamically or instantaneously the antennas are chose to transmit the data. So this is beam steering. So you can see the physical aperture of the antenna is like this. I am orienting the direction of the wave, and this is the steering angle, theta, phi. So this is 2-dimensional. So I'm having theta, planar array means I'll be having 2 angles, that is theta and phi. So random antenna selection, every antenna has the same probability to be chosen. So antennas are chosen arbitrarily and grating lobes are formed in undesired direction. So we can average out the grating lobes by randomness in beam pattern. And the beam width is very, very narrow. and amount of interference with signals for other users can be decreased. So you can see this diagram which shows you the radiation pattern. So first two are for fixed antenna selection, where I'm having a bigger beam pattern, and B diagram shows the fixed antenna pattern where the number of antennas I have increased from 4 to 16. So when I increase the number of antennas, my beam is going to be very, very narrow. The second one is the random antenna pattern for 4x4 MIMO system, and the D is for 16x16. When I keep on increasing the antenna size, my beam is going to be keep on getting narrowed. So my main aim of making the beam narrow is to reduce the grating lobes, to reduce the side lobes. You can see the side lobes are reduced. Yeah. So thank you. So this is my presentation. So if you have any doubts, you can ask.
Participants may ask questions.
Hello, may I speak one? Hello, am I audible?
Yeah.
Good morning, ma'am.
Yeah, good morning.
I'm also working on these antennas.
I'm not able to hear you. Can you please talk loudly?
Yeah. Suppose I have developed an algorithm for this random antenna selection, and,
Yeah.
and I have encrypted some data using this technology. How can I verify whether my algorithm is robust or not? What are the performance metrics for measuring the robustness of the algorithm in microwave, this micrometer technologies?
Millimeter wave technologies.
Millimeter wave technology.
First of all, actually, we are doing this random antenna selection in the hardware. Hardware means in the base station. In the so all these are hardware technologies. Here, of course, we will if I mean this random antenna selection. If we are implementing the algorithm, any algorithm to choose the antenna selection, one thing what we have to keep in mind is the orientation or the angle with which the algorithm should be in a very, very adaptive way, such that it is choosing the and with which it is directing. So that is the very important point. The algorithm should be adaptive also as the user moves. So the algorithm should be fair enough, or it should be dynamic enough to randomize the antennas instantaneously, and the angle of direction also should be chosen instantaneously to reach the receiver.
Okay, thank
you. That is the very important thing which the algorithm should be following. So instantaneously it has to work to choose the antennas, and angle also is very important. At what angle it is directing the beam. So those two are definitely should be followed.
Yes, ma'am. Thank you very much.
Yeah.
There is a question in the chat box. Which technology is more secure nowadays?
Chat. Okay, which technology is
More secure.
more secure? See, all the technologies are having advantages and disadvantages. So we cannot, I mean, as far as this mobile communication is concerned, we are having security issues in different technologies we are having in a different, so we cannot frame a I mean, we cannot frame a benchmark for any technology, but this technology is, I mean, it gives us the highest, I mean, higher security compared to others.
So I think there are no more questions from the participants. So on behalf of Department of Mechanical Engineering, Teaching College of Engineering and a coordinator, and on behalf of participants, I sincerely thank ma'am for taking a wonderful session and for being with us for the session and also for accepting our invitations to participate in this particular FPP. Thank you, ma'am. Thank you so much.
Thank you. Thank you so much. Thank you. I hope I have delivered some information for all the participants who are from different disciplines. So I think I have maintained that line. Thank you so much. Thank you.
Thank you.
Sir, shall I, can I stop sharing my screen?
Thank you.
Yes, ma'am. Yes, ma'am.
Okay.